Okay, let's get started. Excuse me for interrupting. Today I want to talk about two things that are kind of fun to talk about and actually deserve far more discussion than we have time to give them in this course. That is magnetism, and then I'll finish up with superconductivity. Magnetism we talked about last time. The sources of magnetism, anytime you have an unpaired electron, or at any time you have a current circulating, you produce a magnetic field. The simplest and most important sources of current for the purposes of material properties are the unpaired electrons themselves, since the spinning of an electron, as we discussed last time, gives rise to a magnetic moment, which is called a Bohr magneton. In the engineering of magnetism, electrical engineers worry about circulating currents and current loops and solenoids. For the magnetic properties of materials, we're almost always more interested in what in the magnetic moments of unpaired electrons. As I said last time, there are really two parameters we use in magnetization, the magnetic field X and the magnetic flux B, where B is mu 0 H. Mu is the magnetic permeability, mu 0 is the permeability of free space, and just as with the dielectric constant, we set the units, but this, by the way, is rather recent. Until fairly recently, we used a different set of magnetic units. Recently, people have shifted to these units, which have the nice property that the magnetic permeability mu is a dimensionless number which is necessarily greater than 0. So we get a very simple material property. Very often, instead of the permeability mu, we use the susceptibility. If you put a magnetic field on a material, you will develop a spontaneous magnetization inside that material, and the proportionality is mu n is the magnetization in the material, is chi the magnetic susceptibility multiplied by the magnetic field. The relation between mu and chi is just mu is equal to 1 plus chi. So chi can be negative, it can go as low as -1, where mu is a positive definite number. The reason we carry both the magnetic field and well, there are many reasons, but the simple one to keep in mind has to do with the boundary conditions. It turns out that the magnetic flux is continuous, the normal component of the magnetic flux is continuous along a boundary, while the tangential component of the magnetic field is continuous across the boundary. That has the consequence that if you put a magnetized material inside a magnetic field that is normally incident, the magnetic field inside the sample will decrease, so that field plus magnetization is equal to the field outside. Conversely, if you put a sample that is magnetized tangential to a magnetic field, the magnetic field inside the sample will be raised. In this case, you will keep the imposed field, and you will add to it the magnetization of the material. So how a material responds to a field depends quite a bit on how it's oriented with respect to the field because of these different boundary conditions. Well, I talked about diamagnetism and band paramagnetism last time. Let me just say that there are subtle magnetic effects in materials. In particular, diamagnetism, you put a material inside a magnetic field, you induce currents in the material. Those currents will be oriented so that the magnetic loop, the magnetic field they create, opposes the imposed field. So it cuts down the magnetic field in the material. That's called the diamagnetic effect. In most materials, it's very, very small, in large part because of the resistance to this imposed current. The one exception is in superconductivity. If the resistance goes to 0, then there's no limit on the diamagnetic effect, and it becomes just big enough to cancel the imposed field, which is called the Meissner effect in a superconductor. Paramagnetism in general, whatever its source, is the disordered magnetism that we get at high temperature. It's of some interest. You have what's called paramagnetic resonance, which is a useful characterization tool, but it doesn't have that much in the way of engineering importance. So I'll skip that and go to what really matters, which is ferromagnetism. If in the in the case of transition metals and rare earths, where you have an inner orbital that is only partly filled, the nature of the coupling of the spins of those electrons, which partly fill an inner shell, have the consequence that an atom may have a significant magnetic moment. What happens is that these spins tend to align with one another to the extent that they can do that. So if we come down the sequence of transition metals, scandium has only 1 electron, therefore 1 Bohr magneton. Titanium has 2 electrons in its d shell. These 2 electrons will align their spins. So titanium has a magnetic moment of 2 Bohr magnetons. Vanadium has 3. Chromium has actually 5, a huge magnetic moment. And the reason is that in chromium, we not only align the spins, but because of the favorable interaction between those spins, it becomes energetically favorable for the s level, which ordinarily would have 2 electrons, to give up one of its electrons so that we can complete the spin paralleled d shell and get a magnetic moment of 5. So instead of the configuration being 3d4 4s2, it's 3d5 4s1. Manganese also has a magnetic moment of 5. You may wonder why these things that have these huge magnetic moments are not the things we ordinarily think of as magnetic materials. I'll get to that in just a minute. Iron, magnetic moment of 4. Cobalt, magnetic moment of 3. Nickel, magnetic moment of 2. Then we get to copper. The same thing happens in copper as happens in chromium. We can complete the whole d shell, fill all the magnetic states, by dropping one of the 4s electrons down into the d shell. And that happens. Therefore, copper has no magnetic moment at all because all of its d states are filled. And copper has a natural valence of 1 rather than 2, which is what makes it one of the things that makes it such a great conductor. So both of these come from the interactions in the d shell that make it that use the fact that it's energetically favorable to fill that d shell when we can do it. So these are the various magnetic moments. If we were to go to the rare earths, to the f shells, we would find the same effect, but there the magnetic moments can be much larger because there we have 18 states, 9 of each spin to fill instead of 10. So what happens to these spins, these big magnetic moments? And why is it so few of these magnetic materials are significantly useful in engineering? Very simple reason. At high temperature, it doesn't matter what these spins are because they're all disordered. The net magnetic moment at high temperature is 0 unless we put something in a magnetic field, and even in the presence of a magnetic field, the alignment is weak enough that the paramagnetic effect is not that big. So high temperature, nothing happens. At low temperature, these spins will always align. There is always an energetically favorable contribution to their alignment. So at low temperature, we always get magnetic order. However, that magnetic order can happen in 3 ways, 2 basic ways. First of all, the magnetic moments can align. If they align, then you get a local domain in the material where we have a number of atoms where magnetic moments are aligned. You've got big magnetism. That is the ferromagnetic order. Alternatively, they can align opposite. If they align opposite, the magnetic moment is 0. And this is antiferromagnetic order. And it turns out that almost everything in the periodic table prefers an antiferromagnetic ordering. That's why chromium and manganese in the metallic state are not ferromagnetic. They have big magnetic moments, but they're aligned in opposite directions, so there's no net magnetic moment. However, there's a third kind of magnetism, which is what we call a ferrimagnetism. That is a case in which we have not a single material, but rather a material in which there's more than one magnetic moment or more than one state that can be occupied. In that case, even if we have an antiferromagnetic ordering, it may well happen that the two elements in the antiferromagnetic system have different magnetic moments. If all of the big magnetic moments point one way and all the small magnetic moments point the other way, then you will get ferromagnetism even though the basic ordering is antiferromagnetic. The classic example of that, the very first magnetic material known to man, was lodestone. Magnetite, Fe3O4, used in China in compasses and such things. To this day, you go to China, one of the popular tourist items, probably see them here too, is a plate with a spoon on top of it, and the spoon always points to the north. That is a replica of a very ancient type of Chinese compass, and it used limestone, Fe3O4. Fe3O4, despite the fact that it was iron, is antiferromagnetically ordered. But iron, it's a mixture of Fe+2 and Fe+3. They have different magnetic moments, and those magnetic moments are antiferromagnetically ordered, but ordered in such a way that there's a net magnetic moment. And that is an example of a ferrimagnet. It's also the case, when we get to more complicated materials, that there are a number of compounds that become ferromagnetic, even though the elements are not. Gosh, if you were a bit older, you would have used tape for recording music, and the best tape was chromium oxide. Chromium is antiferromagnetic, not very good recording medium. Chromium oxide is ferromagnetic and becomes a good recording medium. There are quite a few, Fe3O4 is an example, there are quite a few materials in this ferrimagnetic case that have the nice advantage that they are oxides. And as oxides, they are simultaneously ferromagnets and electrical insulators. And as I'll discuss in just a moment, there's some huge advantages in having materials that have that property. The so-called ferrites are the classic examples. Ferromagnetism is actually very uncommon in the transition metals, iron, cobalt, nickel. And in fact, in cobalt and iron, only one of the two structures. BCC iron is ferromagnetic, FCC iron is antiferromagnetic. Cobalt, the hexagonal, let me get this wrong, hexagonal phase, it's hexagonal or cubic. I think the hexagonal phase is the ferromagnetic one, only one is. Nickel. Among the rare earths, only gadolinium and dysprosium are ferromagnets, and very powerful ferromagnets because they're out here in the middle of the sequence and have very big magnetic moments. Unfortunately, these are also quite expensive materials. Having a ferromagnetism is not sufficient to have a ferromagnet. And you all know that. If you take just a hobby magnet, pick it up and take a nail, the hobby magnet will attract the nail. But unless you magnetize the nail won't particularly attract another nail, may weakly but not very strongly. Even though it is made of a ferromagnetic material, that is not sufficient to create a ferromagnet. The reason is the following. If I have a material in which all of the magnetic moments are aligned parallel, then I get a significant field coming out of the material and penetrating space. There is an energy associated with that field. So the preferred configuration of any ferromagnet is to make itself up of magnetic domains, such as I've shown schematically here, such that the net ferromagnetic moment of all of these domains is zero. They just cancel each other. As a consequence, if you take a ferromagnetic, heat it up to high temperature, any ferromagnetic material, heat it up to high temperature, cool it down, let it achieve some sort of equilibrium condition, it's going to look like that, it's not going to be a ferromagnet. In order to make it into a ferromagnet, you have to do something to align these spins within the material. And we do that by imposing magnetic fields. Since a magnetic moment will align with an imposed field, we can take a material that has no moment, beef up the field. As we beef up the field, now darn it, I need a pointer, it's not working for me today. The line that starts here at the origin is the initial magnetization curve. As we beef up the field, the magnetization in the material builds up until it hits some saturated value. Now, what happens as we build up that field is that within the material, we have these various domains. The domains are separated by domain boundaries. As we beef up the field, we put a force on those domain boundaries and they move. As the domain boundaries move, the domains grow. And in the extreme case, we can create a situation in which the entire material is is similarly oriented. In fact, the building up to the peak magnetization really has two effects ordinarily. We have to sweep the domain so that we get only one direction. The magnetic direction is usually a particular crystallographic direction. So in order to get the field aligned in the direction that we want it to be aligned, if that's a random direction, we also, having aligned all the axes, then have to rotate them into the proper direction. Both of these things give rise to this magnetization. Now what happens if I then let the field go, take the field off, drop it to zero? What will ordinarily happen is that there will be some decrease in the magnetic field, particularly this alignment effect will go away. But I will have left a significant or possibly significant field, which is called a remnant magnetization. Saturation magnetization is the most magnetization the material can have. The remnant magnetization is the magnetization it has after I take the field off. Why is there remnant magnetization? Well, in order to get back toward the initial configuration, these magnetic domains have to form and grow again. But now they're growing, they're not being pushed by the magnetic field. They are moving spontaneously under whatever thermal forces are available. And just about anything there is in the microstructure, any non-magnetic solute, any defect like dislocations, grain boundaries, various other such things, will interact with these domain boundaries and make it difficult for them to move. So they rather quickly, in some cases, get pinned. And where they are pinned establishes what the remnant magnetization is. Now suppose we want to get rid of the remnant magnetization. What we have to do is to put on a reverse field, move the field negative, and push those boundaries back until they cancel each other out. That's what's called the coercive field, HC. And of course, the higher the coercive field, the more difficult it is to get the magnetization back to zero again. That is the field that is required to push and reconfigure all these domain boundaries until we get back into this equilibrium situation. So that's the coercive field. Then of course, if we want to reverse the field, we can reverse it to full saturation, but we have to push the field even further to cause that to happen. And if we were to then reverse the field again, we would generate this loop. This loop is called the hysteresis loop. And if I take a magnet and I put it in a cyclic field that takes it all the way from saturation in this direction to saturation in that direction in the opposite direction, it's going to cost me energy, an energy measured by the area of that hysteresis loop every time I reverse the field. And that is a huge business in the whole wide world. A significant fraction of all of the energy produced in the United States goes into flipping magnetic fields in various electronic devices such as generators and transformers and such things. So this is a very big deal. Well, there really are two kinds of magnets that we identify. And we identify them on the basis of this hysteresis loop and the remnant magnetization. The first and the simplest for you, most familiar to you properly, are what we call the hard magnets. A hard magnet is a magnet that will retain a magnetic field. If you want to make magnets to use in children's toys or to lift scrap metal in a junkyard or to act as memory elements in memory devices, you want things that you put on the magnetic field and it will stay there. It's not going to go away. Those are hard magnets. For a hard magnet, you want a hysteresis loop that looks like shown here with a very high remnant magnetization and a very big coercive force because you want it to be very difficult to get rid of that magnetization. I remember we used to do tests at the National Magnet Lab, which was then located at MIT. It's been Florida State for years now. They would have these big 12 Tesla magnets in which we were doing various superconductivity experiments in those days. And the first thing that you would be told, and we all forgot and all paid the penalty, is that you had to take out your wallet with all your credit cards in it and leave it about 100 yards from where these big magnets were, or you would not have credit cards anymore that anyone could read. It works the other way too. When the BART trains first started running out here, some clever, probably engineering students, Berkeley students, I don't know if they were caught, discovered that with a hand iron, you could magnetize a BART ticket so you put back in whatever value you got erased. So they got free rides until people caught up with them. So these are hard magnets. Some of the classic hard magnets, Alnico was, for a long time, the hard magnet until they came up with Sendai dust, samarium cobalt at Tohoku University in Sendai in Japan. I saw one of the first examples of this when I was visiting Tohoku long before you were born. And the first application they put out, well, there were two really. It was a huge commercial application because you really needed a hard magnet to make miniature speakers for small radios and such things. So that was the commercial application. But the kind of public application he came out with was women's earrings. And the earring, you put whatever earring you wanted, but instead of piercing your ear, you just had these two magnets. You just put them on the inside of your earlobe, and it would stay there. They were pretty strong. I haven't seen those on the market for a very long time, so I think they're long gone, but it did exist. The even better one was produced actually General Motors. They need hard magnets for automobile starters. I don't need to go into here why, but they do. And they produced the neodymium iron boron, Fe14 indium 2 boron, which was an even better permanent magnet. I once got involved in a patent controversy involving that, which had nothing to do with automobile starters. Some guy had made sunglasses, and the sunglass frame, you just attach the sunglasses over your eyeglass with this little magnetic spots, and you use neodymium iron boron for the magnetic spots to hold the sunglasses on. They work very nicely. But someone else was making the same thing with a slightly different configuration, and a huge patent suit broke out, and these guys really mad at each other, in which I got peripherally involved. One of the problems with these things, which kind of killed the eyeglass market, I could see it happening, but they wanted to fight anyway, is this neodymium iron boron is really unstable. It corrodes like crazy in air. So if you want to do something like a sunglass attachment, it works fine until you kind of scratch the little surface and then it's gone. So the durability of these is not very high. I don't know if they make them now or not. You could coat it so that it would work. In order to get this kind of behavior, you need something that has a very good natural magnetization, but that's not enough. You need to throw in barriers, things in the microstructure that will keep those domains from moving and give you good hysteresis, and therefore big remnant magnetization and a big field. One of the best examples of that was done by actually one of the first students I had, who subsequently was a guy who set the record for the most patents at Bell Telephone Laboratories. Sung-Ho Jin is now at the faculty in UC San Diego now. But he went up there. They had a problem. They had constraint on their material. They couldn't go to these things. They had to make something that was a very, very strong ferromagnet, great hysteresis. So what he did was to use, we talked briefly about spinodal decomposition. Take a material, make it chemically unstable, and will spontaneously develop a very local segregation in the material. Well, he took it's called chrome indoor, it's iron chrome, I forgot what all was in it, which had a spinodal decomposition such that as the composition changed locally, one of the two compositional regions would go ferromagnetic and the other would not. So he could create this sample that had a very dense distribution of very tiny ferromagnets. It was very hard to flip them as a consequence, very good strong magnets, and there was something like 2 billion telephone headsets made with that magnet sitting in them, so it was a very important breakthrough. I'm sorry? It's called chrome indoor. It was invented at Bell Labs in the early 1980s. Sung-Ho Jin and Gil, I'm not drawing a blank on Gil's last name, but the guys who put it together, one of these days, I'll remember what Gil's last name was. Sung-Ho I know. He's around occasionally, he comes up here every now and then. Hard magnets, one of the biggest applications in recent years, of course, has been for magnetic memories. Here you take the direction of magnetization. Remember, anytime you have a readable element, a controllable readable element, be it a transistor on-off, a switch on-off, or a magnetic moment up-down, that is, you can do binary math with that. Because up can be 1, down can be 0, or vice versa. There are other games you can play in which you use the change in the magnetic moment to indicate the end of a chain of digits, so you can actually get denser packing. But basically, what magnetic memory does is use a ferromagnetic element in which one direction signifies a 1, the other direction signifies a 0. For a variety of reasons that have to do with the manufacture of these magnetic films, it was much easier to create what we call parallel recording, in which the magnetization is in the plane of the film, than it was to do perpendicular recording. As it turns out, perpendicular recording can be much denser. Several times as much information can be put on a film that uses a perpendicular magnetic field and a parallel magnetic field. And so this is what really super high density current magnetic memories use. The smaller the domain of the magnet, the harder it is to flip the magnet. And you can kind of see that. If I get a very small particle, the easy way to flip a magnet is by moving domain boundaries in the material. But there's kind of a minimum domain size because the surfaces, these domain boundaries have a surface energy associated with them. And you start trying to make one thing really small, the surface energy is so big the domain doesn't want to form. So if you get a small enough magnetic particle, it doesn't form domains. The only way to flip it is to flip all the magnetic moments at once. This is a hard process. So small particle size automatically creates a very hard magnet. And this was the secret of the chrome indoor I was just describing you. By spinodal decomposition, you can take a solid material that make it have many, many tiny domains, which are your magnetic domains. And that, of course, is what you do in magnetic media. You make very, very small particles or very, very small regions, which are magnetized and are difficult to flip. The harder they are to flip, the more retentive your magnetic medium will be. Of course, you have simultaneously the other end of it. In most magnetic media, like the ones you use in your computer, you not only want them to retain that memory, but you want to be able to write. You want to be able to change the memory. So you're fighting this constant battle of give me a hard enough